In this video, we will continue to learn how to determine if the molecule is chiral or achiral in a step-by-step process that makes it much easier. In the last video, I already showed the chart that I use, but we will go over it here again. So in order to determine whether your molecule is chiral, you have to ask the following questions. The first one is, are there any stereogenic centers? There are different names for these. Sometimes they're called stereogenic centers, stereogenic carbons, chiral carbons, and so on. But basically, it's a carbon that has 4 different groups, and we will go through that when we do our examples. If the answer is no, there are no stereogenic centers, your molecule is achiral. Please keep in mind that there are exceptions to this rule. There are molecules that don't have any stereogenic centers and are achiral, but those are exceptions, and for the most part, you can say that if your molecule does not have a stereogenic center, it is achiral. If their answer is yes, the next question you ask is, are there 2 or more stereogenic carbons? I call them carbons, here are centers, it's the same thing. If the answer is no, your molecule is chiral. If their answer is yes, the last question you have to ask is there a line of symmetry that cuts the molecule in half with 2 identical halves? Now, your line of symmetry doesn't have to be vertical, it could be horizontal, diagonal, etc. As long as it cuts your molecule in half with 2 identical halves, that means that you have a line of symmetry, and if that is the case, if the answer to this question is yes, you have a special case of the molecule. It's called meso, and meso molecules are achiral. If you do not have a line of symmetry, then your molecule is chiral. Just to let you know, the official definition of chirality is that a molecule is chiral if its mirror image is non-superimposable. So this chart, non-superimposable means that they cannot be aligned. The molecule and its mirror image cannot be aligned, just like our hands cannot be superimposed on each other, the left and right. And so our hands are chiral. And so the molecules, when you draw its mirror image, they cannot be superimposed on each other. They will not match, and so those molecules are chiral, but it's really hard to do 3-dimensionally, and that's why I did this chart. However, if your teacher asks, why is this molecule chiral, the answer is because its mirror image is non-superimposable. Now, with that in mind, let's make a use of my chart and do some of the questions. We already did some of these questions in the last video, and I will continue with the harder ones in this video. We will start with B. Again, this question, if we are going to determine whether the molecule is chiral or achiral, we're not going to do the RNS here. We will do it in a separate video. So the first question is, are there any chiral carbons? Now, if we look at this carbon, it's attached to CH3, a hydrogen, because it must have 4 bonds, and it has only 3, so that means the 4th one is hidden. It's a hydrogen. Hydrogen, methyl, alkyl on this side, 2 carbons on this side, and here this group is definitely different from this group, so this carbon is a stereogenic center, chiral carbon. This carbon, same, it's attached to methyl, a hydrogen, ethyl on this side, and this group on this side, stereogenic center. So let's go through our questions. Is there a stereogenic center? Yes. Are there 2 or more stereogenic centers? Yes. So the next question we have to ask is there a line of symmetry? Sometimes your professors will give you a tricky molecule like this one, where it kind of looks like the molecule is symmetrical. However, if you notice, my methyl groups and my ethyl groups are not aligned with one another. They're not. This ethyl group is going up, this one is going down, my methyl here is going up, here is going down, so they're not aligned. So what do you do to figure out the line of symmetry? You must first rotate the molecule around this single bond. I'm going to rotate the right part, so I'm going to keep the left part. I'm sorry. I meant I'm going to rotate the left part, and I'm going to keep the right part the same. So let's go ahead. So this is still a wedge, Now, this is a trick that I use. My methyl here, it's going, it's going down, and so when I rotate around the single bond, it's going to go up. Now, if this was a wedge and I rotate and it was down, it's going to be up as a dash. So you can switch the stereochemistry. This was down, wedge, I rotate, now it's up, dash. And this is my ethyl group attached to it. So now everything is aligned. Notice the two methyl groups are aligned with one another, and the other groups are also aligned with one another. Now, and only now we can ask, is there a line of symmetry? And the answer to this is no, because my methyl groups are not the same. This methyl group is a wedge and this methyl group is a dash. They're not the same, therefore there is no line of symmetry. Therefore this molecule is chiral. Okay. Now, so this one was a tricky one. It kind of looked like there was a line of symmetry, but it was necessary to rotate around the single bond until all of my groups were aligned with one another, and then to see if there is line of symmetry, and there was no line of symmetry because the two methyl groups were opposite. Now let's do part Z. Part Z, again, we have to ask, is there a chiral carbon, stereogenic center, whatever you want to call it? And yes, this carbon is going to be stereogenic because it has fluorine. It has hydrogen that was not written because it must have 4 bonds. And this group are certainly different. I have fluorine on the right, methyl going on the left. So it is a chiral center, chiral carbon. And here, same thing happens. Fluorine, hydrogen, carbon with the fluorine on this side, carbon with the methyl. So I have 2 chiral carbons. Now, the next question is there a line of symmetry? So first of all, we must say they're not aligned with one another, so we can rotate again. Another thing that we can notice that will help us even without rotating is if we look at the double bonds. This double bond, we can see that the two methyl groups are opposite of one another. And this double bond, the two methyl groups are on the same side. So if I put like a little dotted line through the double bond, these two are opposite of one another. But if I put the little dotted line here, these two methyl groups are on the same side of one another. So no matter, because I cannot rotate around the double bond, no matter how I will rotate this molecule, my two halves will not be able to align. This molecule will not be symmetrical because on the right side I have a double bond where two methyl groups are opposite of one another. And on the left side I have a double bond where two methyl groups are on the same side with one another. And therefore this molecule is chiral as well. I hope you enjoyed this lesson, and I look forward to seeing you in more of my organic chemistry and general chemistry videos. And I hope you really enjoyed it. Thank you.